Hi students, welcome to Sunil's tutorial. I am Sunil Mirwani and today we will be doing this chapter called as UCM. We are going to today see vertical motion. We've so far seen horizontal motion. Let us try to understand vertical motion of a body. Right? Let's consider that a body is moving in UCM. Let's assume that this is the center. Okay, let's consider these points as A, E, C and F. The body is moving anti-clockwise. Okay, now let us assume that OA is my radius vector. Now a body is vertically hanging downwards. Let's assume that I move the body by a certain angle. The body now is at this position such that it has covered an angle of theta. Right? Now we know that this whole distance OA is radius. Let us assume that this distance, it has moved up by a distance of h. If this distance is h, then the distance ON will be r minus h, the total distance minus h. This is r, right? Now what are the forces that are going to be acting at this point? One, the weight that will be acting vertically downwards, that is mg, right? Now and you will have the tension on the string T. Okay, now let's write all this down theory first before we move on to the actual derivation. I can say that consider a particle of mass m suspended from one end of a string. Of length r. So mass of the particle is m, length of the string is r, and let us assume that let initially the particle be in rest at point A. Initially particle is at rest at point A. Right? Now let us assume that it is given some initial velocity u. Right? Let it be given initial velocity u. Let us assume that u is the initial velocity given to it, right? So that it starts moving in the vertical plane and let it reach point B. Reach point B. This is your point B, right? So the body has reached point B and has covered an angle of theta. Let us assume that it covers an angle of theta at the center, right? Let us also assume that length AN is equal to h, right? Now, if the body is in equilibrium at point B, consider equilibrium position of the particle in B. Now if B is the equilibrium position, now let's try to find out the forces that are going to be acting on the body. One, the weight of the body, mg acting downwards. I can say that in this position, the forces acting on the body R first, mg, that is the weight of the particle acting downwards, that is the weight of the body acting downwards, and 2, T, the tension on the string acting on BO. T, tension on the string acting on BO, in the direction of BO, right? Now the weight mg, since it's a vector quantity, it can be resolved into two components. Guys, let's see this. The weight mg can be resolved into two components, one along horizontal and one along vertical. This is one component, this is the other component, right? This is going to be mg cos theta, where this angle is theta, and this is going to be mg sin theta. So thus the weight mg can be resolved into two components, right? The weight mg can be resolved into two components. One will be the mg cos theta, that will act along BO but in opposite direction and will counterbalance the tension on the string, right? The component mg cos theta acts along OB in opposite direction, that is opposite to the tension T, right? Hence the difference provides the necessary centripetal acceleration. Hence the net tension on the string now is going to be the difference. Hence the difference. What is going to be the difference, guys? See the figure. This is tension T acting in upward direction. Mg cos theta is acting in downward direction. So what will be the net force that will be acting in upward direction? The net force that will be acting in upward direction will be T minus mg cos theta. Now since it is acting in upward direction, it is acting towards the center. That means it has to be centripetal force. Therefore, the difference between the two is going to provide the necessary centripetal force, right? Hence the difference T minus mg cos theta provides the necessary centripetal force, mv square by r, right? Therefore I can say that T minus mg cos theta is equal to mv square by r, right? Where v is the velocity of the particle at point B. Now let's look at the other component. The other component mg sin theta acts tangentially in the direction opposite to the velocity. The component mg sin theta acts tangentially in a direction opposite to velocity v. Now guys, let's see the figure. Remember when the body was at A, we gave it an initial velocity u. Now by the time the body reaches B, its final velocity becomes v and the body is supposed to move in this direction with v, right? Now if you look at mg sin theta, it is exactly opposite to the velocity v, right? So it is counterbalancing this, right? Now we also have seen that an is h. So I can say by kinematical equation, says that v square is equal to u square plus 2gh, and g is negative, so minus 2gh. G is always considered as negative. Now, in that case, I can substitute this value of v square, let's call this as equation 2. In this equation 1, I can substitute v square in equation 1. Now, if I substitute v square in equation 1, then in that case I'll get t minus mg cos theta is m by r v square. V square can be written as, we just found out, u square minus 2gh. Right? Now, can you all please see the diagram again? Look at the diagram. What will be cos theta in this diagram? See, if this length is h and the whole length is r, that means ON will be r minus h. Cos theta is adjacent upon hypo. That means cos theta should be r minus h upon r. Right? So I can say that in triangle ONB, cos theta is r minus h upon r adjacent upon hypo. Right? Now, if I substitute this value in my equation of t, I will get t minus mg. Instead of cos theta, I am writing r minus h upon r is m upon r u square minus 2gh. Right? So in that case, I could say that, take this on the other side, I would say that t is equal to m upon r u square minus 2gh plus mg r minus h upon r. Now here I could take m upon r common. If I take m upon r common, I'll get u square minus 2gh plus gr minus gh. Right? So in that case, I will get this as tension on the string is going to be m upon r u square plus gr minus 3gh. So that is the tension that acts on the string when you try to move a body in vertical motion. Right? Do you understand? So if they ask you to find out the tension on the string, this is how you derive the expression for tension on the string. Now, let us try to consider special cases for this. When the particle is at lowermost position, A, particle at lowermost position A. Now if the particle is at lowermost position A, then h will be 0, because this distance, guys, as per the figure, if it is at this point, then h is going to be 0. At lowermost position A, h will be 0. If h is 0, then tension will be equal to m upon r u square plus gr. That will be the total tension that will be acting on the string. Right? We will call this as TL, tension at the lowermost point. Now let us assume that you have rotated the body and the body is at uppermost point. Particle at uppermost position C. Right? Now if the particle is at uppermost position, guys, look at the diagram. From A, the body has moved to C. That means what is the height that it has covered? This plus this. This height is r and this height is also r. So for uppermost position, h will be equal to 2r. Substitute in the equation of tension. So tension at highest point will be m upon r u square plus gr minus 3g h. H can be written as 2r. So therefore this can be written as m upon r u square plus gr minus 6gr. So this will be m upon r u square minus 5gr. So the tension on the string at the highest point will be u square minus 5gr. Fine, do we get this in here? Now, what is the difference in the tension between the highest point and the lowest point? I can say also tension at the difference between the tension between the lowest and the highest point is going to be nothing but m upon r u square plus gr minus m upon r u square minus 5gr. M upon r I can take common, so this will be u square plus gr minus u square minus into minus plus 5gr. So u square and u square gets cancelled, so this is going to be m upon r gr plus 5gr, that is 6gr, but r and r gets cancelled, so 6 mg. The difference on the tension on the string between the lowest point and the highest point is 6 times the weight of the body. Fine, do we get this thing here? Now that we know the tension, let us find out the velocities. Velocity. Let's find out the velocity at the lowermost point. Let's find out the velocity at the lowermost point A. Now, we know that when the body is rotating, when the body reaches the highest point, then its velocity has to become 0. Guys, the body starts rotating from A, it moves up and it reaches C. At point C, its velocity will be 0. That means that tension at the highest point is going to be equal to 0, because the entire weight of the body is going to be directed downwards. I can say that tension at the highest point you had found out is m upon r u square minus 5gr. But at the highest point, we know that when the particle has just crossed the highest point without slacking of the string, th is 0, but th is equal to 0. So in that case, I can say 0 is m upon r u square minus 5gr. So 0 is equal to u square minus 5gr. So u square is equal to 5gr. So if you want a body to move from bottom right to top, then this is the velocity that you have to give it. So you can therefore say that u is square root of 5gr. Right? Thus, the velocity, initial velocity at point A is going to be square root of 5gr. That is the initial velocity that should be provided so that the body starts from bottom and reaches the top. Right? Next, let's find out the velocity at the uppermost point. Second, velocity at uppermost point. Let's try to find out the velocity at the uppermost point. Now, velocity at the uppermost point. At the uppermost point, h is equal to 2r, because the body has covered a distance of 2r. Now, by kinematical equation, I can say v square is equal to u square minus 2gh. H can be written as 2r, so I can say v square is equal to u square minus 2g into 2r. So v square is equal to u square minus 4gr. Right? But we have just found out u square as 5gr. You just found out, guys, see this here. You just found out that u square is 5gr. So I'm substituting this value up there. So in that case, I'll get v square is equal to 5gr minus 4gr. V square is equal to gr. So v is equal to square root of gr. So velocity at point C is going to be square root of gr. So that's the velocity of the body at the highest point, and this velocity is also called as the critical velocity. That's the minimum velocity that the body should possess so that the body completes a circle. Otherwise, the string will slacken and the body will straight fall down. Right? Now, let us find out the velocity at horizontal level. Velocity at horizontal level. Now, When the body has reached horizontal level, guys, can we see the figure? The body starts from A and reaches E. If the body starts from A and reaches E, what is the distance that the body has covered? It has covered a vertical distance of R. So at horizontal level, H will be equal to R. Again, I could use kinematical equation. If I use kinematical equation, I can say V square is equal to U square minus 2GH. V square is equal to U square. U square can be written as 5GR minus 2G. H can be written as R. So V square is equal to 3GR. Therefore, V is root of 3GR. So at horizontal level, the velocity of the body is 3GR. So therefore, I can say that the velocity at point E is square root of 3GR. Now that we have found out velocity, then we can find out the acceleration also. Velocity we found out, right? Now let's try to find out the acceleration at various points as the body rotates in vertical circle. Now at point C, that's at the uppermost point. At the uppermost point, centripetal acceleration. We have just derived that centripetal acceleration in the previous lecture, if you see, is nothing but V square by R. So acceleration at point C will be velocity at point C the whole square into R. We also derived that velocity at point C is nothing but square root of GR the whole square upon R. So that is going to be acceleration at point C will be nothing but GR upon R. So that will be nothing but G. That is going to be the acceleration at point C. Right? Next, at point, let's find out the acceleration at point A. Acceleration at point A will be velocity at point A the whole square divided by R. Now velocity at point A, that's at the lowermost point, we found out is nothing but square root of 5GR the whole square upon R. Therefore acceleration at point A is going to be nothing but 5GR upon R, that is 5G. That is the acceleration at point A, right? Next, what is the acceleration at horizontal level? At point E. At point E, it will be velocity at point E the whole square divided by R. Velocity at point E we found out is square root of 3GR the whole square divided by R. So acceleration at point E is going to be 3GR upon R, which is nothing but 3G. So that will be the acceleration at various points, at the highest point, lowest point, and at the center level point. Now that we have found out acceleration, you can also find out the total energy. Acceleration. Let's find out the total energy. Now total energy at point C. Now we know that total energy is the sum of potential energy and kinetic energy. Therefore I can say that total energy is potential energy plus kinetic energy. Now potential energy at point C, potential energy is nothing but mgh. Kinetic energy is half mv square. At point C, that means vc square. But velocity at point C is nothing but square root of gr. So in that case, but at point C, velocity is nothing but square root of gr and h is equal to 2r. Substitute these values, so you will get total energy is going to be mg, h can be written as 2r plus half mvc square root of gr the whole square. So this is going to be 2 mgr plus half mgr, right, because root and square gets cancelled. This is 5 minus 1, so that is going to be 5 plus 1, sorry 4 plus 1, 5. This is going to be 5 mgr upon 2. So the total energy of the body at point C is going to be 5 upon 2 mgr. Now let's find out the total energy at point A. Total energy at point A. Total energy is potential energy plus kinetic energy. Potential energy is mgh, kinetic energy is half mv square, but at point A. At point A, what will be the value of h? The value of h will be 0, and at point A, we have found out that velocity at point A is nothing but square root of 5gr. Therefore, I can say total energy is m into g into 0 plus half m square root of 5gr the whole square. Right, so this is going to be nothing but 0, 5 upon 2 mgr. That means at point C and at point A, the bodies possesses same energy. Let's also, that means kinetic, that means the energy is conserved. Whether it is at the lowest point or the highest point, the total energy in the body is same. Right? It's only that there is a change in the potential energy and kinetic energy. Right? I've already shown you how to get the potential energy and kinetic energy while doing the calculation of total energy. So you would know which is changing. Like in the case of at point C, your potential energy is 2 mgr and kinetic energy is half mgr. Whereas at point A, your potential energy is 0, whereas your kinetic energy is 5 by 2 mgr. Right? So potential energy decreases, kinetic energy increases, as a result of which total energy is conserved. Fine, do we get this thing here? This finishes this chapter. We'll stop this here for the day. Thank you very much. We have only numericals remaining, which I'll see in the next lecture. Okay, thank you.